So frame structure, same. Any arbitrary loading. I have a distributed loads. I have a horizontal loads. Any arbitrary loading. Take it, scale by 2. Flip 180 degree. Add up, symmetrical load. Subtract, anti-symmetrical load. Sum up, go back to the original. Okay, more example. Here I have this loading, vertical, horizontal. So scale by 2. Flip 180 degree. Then add up. Subtract. If you add this two up, go back to original. So this shows you how you can decompose any arbitrary loadings to symmetrical plus anti-symmetrical loads. So what is the purpose of that? Well, the purpose is that we can utilize this force decompositions onto a symmetrical structures. A symmetrical structure has a nice property that if you flip 180 degree, it doesn't matter, right? So we can utilize this symmetrical structure under symmetrical loads conditions to simplify. And also, you can use symmetrical structure under anti-symmetrical loading conditions and simplify. So this is what we will do. If you have a loading acting on a symmetrical structures, instead of directly analyze it, we can split the loading into symmetrical plus anti-symmetrical, and then do a separate analysis. And eventually superimpose them, get back to the response that you're looking for. So what is the advantage of that? Why don't we just do one analysis? Why do we have to do two analyses? Well, let me show you. Basically, it's different, slightly different. So this is a symmetrical structure under symmetrical loads. Let's see the behavior. So you're anticipating that the deformation goes like this, and symmetrical, it will be a symmetrical deformations, right? So this side and that side will be identical, mirror image. At the midpoint, we noted that at the midpoint, moment and vertical displacement are not equal to 0. You have moments and you have vertical displacements. But the slope is equal to 0. Slope is equal to 0. And actual displacement is equal to 0. Okay? So we notice that at the midpoint, we have such a properties. Now, such a property actually is exactly the same as this kind of support. So this kind of support, you allowed this point, this side, to go down vertically. And this kind of support also prevent these positions from having slope. Slope is equal to 0. However, it will have some sort of bending moment coming from the support. So bending moment is not equal to 0, and displacement is not equal to 0, but the slope is equal to 0. So instead of analyzing the whole structure like that, you can actually analyze half of the structures. You don't have to analyze the complete structure. Okay? So you just do a proper support change at the midpoint. And then you just do half structure analysis instead of the whole structure. Of course, for a simple structure like this, you don't bother. You don't need to. You don't need to do that. This is too simple. You don't need to do that. Now, the thing is, when you get to complicated structures, you can utilize the same concept and try to cut down your analysis by half. So, for instance, I have a frame structures, hinge and hinge there. Everything's are the same, left and right. Loadings are symmetrical. So symmetrical structure under symmetrical loads, the deformations goes like that, and you find out that at the axis of symmetry, there, you have a property of slope equal to 0, horizontal deflection equal to 0, vertical deflection not equal to 0, bending moment not equal to 0, just like what we just saw in the previous slide. So you can just cut the structure into half. You analyze half of the structure only, but changing the boundary conditions there so that it complies to what we observed from the symmetrical structure under symmetrical load conditions. So you just analyze half of the structures like that with this kind of support conditions. So you don't have to go all the way. You just half. All right, so take a look at this one. It's the same thing, symmetrical structure, symmetrical load. So deformation will goes like that, and then you identify here, this point, slope is equal to 0, horizontal deflection equal to 0, vertical deflection not equal to 0, and the boundary conditions can be translated into that. And you just cut this column properties into half and analyze this half of the structure. Okay, hopefully you can simplify your calculations, hopefully. For simple structures, you don't need to do that. Now, how about the other type? Symmetrical structure under anti-symmetrical loads. So here is a symmetrical structure, and the loadings are anti-symmetrical. So you flip and then change side, go back to the original. So this is anti-symmetrical loads. So you can imagine that deformation will go something like this. The deformations will be anti-symmetrical. Yeah? The structure is symmetrical, but loading is anti-symmetrical. So can you anticipate that deformation will be anti-symmetrical? So you flip the structures 180 degree, change sign, the deformation should be exactly the same. So deformation is anti-symmetrical. So take a look at the midpoint there. So what is happening at the midpoint? So midpoint, you can observe that I have a curvature, positive curvature there, and I have a negative curvature there. And in between is zero curvature. Right? Can you anticipate that they will have a zero curvature there? This is positive curvature, this is negative curvature, so in between is a zero curvature. Zero curvature means moment equal to 0. So the conditions at the midpoint is moment and vertical displacement equal to 0. But slope is not equal to 0. Okay, so actually we can take these kind of conditions and then substitute it with a proper support conditions. So we just cut the structure in half, take out the structures with this kind of properties that we observed. The proper boundary conditions that is compatible to this is simply just a simply supported condition, a hinge condition. A hinge condition tells you that moment should be equal to 0, displacement is equal to 0, but the slope is not equal to 0. So if you have a symmetrical structure under anti-symmetrical loads, you find out that that midpoint actually is the same as simply supported conditions. So you just take the structures like that and analyze the structures. Yes? Roller support is the same. Now, we don't have horizontal conditions anyway. All right? So that's kind of magic, huh? You don't have to analyze the whole structure, just analyze half of that. Okay, so if you go to two-dimensional frame structures under anti-symmetrical loads, if the frame is symmetrical, then the deformations will be similar to what you saw just now, but they will have some sort of translations involved. So here is loading, and this is symmetrical structures. So it's going to be translating to the right, but you will have positive curvature, negative curvature. In between, you have zero curvature, no displacement vertically, but you can have translation horizontally. And slope, of course. Slope is not equal to 0. So that kind of conditions actually is the same as the roller support. So roller support, bending moment equal to 0, displacement equal to 0 vertically, horizontally is free to rotate, it's free to move, and slope is not equal to 0. So it's the same as roller support. So instead of doing this analysis, you just do that analysis. And the other half is anti-symmetrical. Okay, so this is how we do it. For structures like this, vertical loads, this is strictly not symmetrical structures. It should be, it should not be it's not a strict symmetrical structure because of the boundary conditions. But because we don't have horizontal force, so it's okay. We can consider this as a symmetrical structure. So symmetrical structures and under loading, the loading is arbitrary. It's not symmetrical. It's not anti-symmetrical. So you can first decompose your loading to symmetrical loads and anti-symmetrical loads, following the procedures. And then you do symmetrical loads analysis first. And you identify this is symmetrical loads and structure is symmetrical. So you just do half the structure analysis like that, putting a proper boundary conditions. Now symmetrical structures, symmetrical loads, so it can move vertically but not horizontally. So the boundary condition become roller like that. So just do that analysis. And because it's symmetrical low symmetrical structures, so the results can be mapped to the other side. So the results here can be mapped to the other sides like a mirror image. Now, this is anti-symmetrical loads. So anti-symmetrical loads, you just cut the structure in half, and you're anticipating that it's going to see some sort of roller, and vertically it's going to be constrained. So you do half of the analysis, and after you are done, you just map it back, mirror image, but with a negative sign. Right? Anti-symmetrical is mirror image and negative sign. So you just flip over there and then change the signs of the force. So originally, you might have a tensions, compressions, then this becomes tensions. So the sign has to be flipped for anti-symmetrical loads. So after that, you just add this one with that one. Then you get this one. Of course, again, you don't do that on a very simple structure. You don't do that on deterministic structures because it doesn't give you any advantage. This is a deterministic structure. You don't need to do this kind of sophisticated operation. You can just directly do a deterministic structure analysis, right? No problem. This is just the illustrations, how you can do it. Now, this structure, take a look. Climb, climb, and roller, roller, roller. So it has 6 degrees of indeterminacy. 6 degrees of indeterminacy. Hello? You coming to play phone? So 6 degrees of indeterminacy. First, you decompose the loading. Now, the structure is symmetrical. So you decompose loading into symmetrical loads and anti-symmetrical loads. So you use the concept, cut the structure in half, like that, and utilize the properties there. The property there is no slope. Slope is equal to 0. No displacement. And bending moment should not be equal to 0. So it turns out that the conditions leads to climb conditions. So you analyze that structures instead of the whole structures there. So this is symmetrical conditions. So that condition is actually 4 degrees of indeterminacy. Now, the other one is anti-symmetrical loads. Anti-symmetrical loads. So again, you cut the structure in half like that. Utilize the property there. You have a slope. You don't have any bending moment. Right? And then no vertical displacement. So the conditions becomes like that. So this is how many degrees of indeterminacy? Oh, I'm wrong. This is 2 degrees of indeterminacy. I'm sorry. This should be a 2 degree of indeterminacy. So you are resolving originally 6 degree of indeterminacy to a combination of 4 degree indeterminacy plus 2 degrees of indeterminacy analysis. Okay, so you need to do 2 analyses, of course, but the degree of indeterminacy is less than before. So you have an options. If you want to stay in the original domain or go into this kind of going to this domain of simplifying, but you need to do 2 analyses. Okay, so this is a concept that we can use to sort of simplify the requirements on the indeterminacy. So some example like this: loading, symmetrical load, anti-symmetrical. And symmetrical load, you cut the structure in half, analyze this half with the proper boundary conditions. And anti-symmetrical load, again, you cut the structure in half and put the corresponding boundary conditions. And you do this 2 analysis instead of that analysis. Okay? But either one, you cannot do it, right? It's still very complicated at this stage. All right, so get down to the real analysis technique now. Now, previously just concept, right? So you can use that concept on any techniques as long as you have the symmetrical structure conditions. So we're going to show you a few techniques that you can use to analyze indeterminate structures. So these techniques are classified into force methods and displacement methods. So force method will be covered in this chapter, chapter 10. Displacement methods will be covered in the next 2 chapters. So that pretty much wrap up the remaining part of this course. So we'll be focusing on how to analyze indeterminate structures. Again, 2 methods. One is a force method, the other is displacement methods. So what is a force method? Force method means that you are choosing force as your starting point. So you use force to begin your analysis as your unknown. So the first approach that we can do is so-called compatibility approach. Compatibility approach. So what is a compatibility approach? It's actually a very straightforward approach. More straightforward than sleeping in the class. Hello, wake up. 好辛苦你. Hey. Good morning. Don't come here to sleep, please. You don't need to come. You see, a lot of people are not here. You don't need to come. So what is a compatibility? The concept is very easy. Here, I have a loading P. This is 1 degree indeterminate structures, 1 degree indeterminate. So what does that mean? It means that I have 1 too many. 1 too many. But 1 too many means that if that redundant, so-called redundant, is known, then I can solve the structures. You only need 1. You only need to solve 1 force. So for instance, if I solve this force, this is a roller support. This is climb support. So if I know this magnitude, I can solve the other three forces there using equilibrium. So 1 degree indeterminacy means that I have one unknown too many. So if I just solve that one unknown, then the structure is solved. Okay, so how do we solve this unknown? How do we solve that unknown? So this unknowns actually, for the force methods, is force, of course. So that is a force. So can you imagine that temporarily, let's forget about this support. Let's assume that I have a P force and By force acting on the structures. So I have two forces acting on the structures. One is P, downward. The other is By, acting upward. So I can use superpositions to analyze the structures. So I analyze P force first, assuming that By is not there. So I can calculate these displacements. This is deterministic analysis, right? Determinate structure analysis. And then I forget about P, I add on By, and then calculate this displacement. So superpositions means that original condition is you have a P force, you have a By force. So all you need to do is just add this and that up. Then you have the original conditions, right? So then you enforce, after you add this two up, you enforce that displacement there has to be equal to 0. Then you will find the so-called unknown force By. So that's called compatibilities. So in other words, it goes like this. This is a force that pushes this point downward, and how much force is required to push this point back into the original positions. Right. So that's called compatibilities. So in operation, this is what we can do. So you identify the so-called redundant force first. So this is so-called redundant force. And redundant force is remove first and calculate the displacement at certain locations under actual loads, external loads. And then remove the external loads, apply this redundant force, and then calculate the deflections again. Of course, there's a trick. Now, the trick is you don't know this redundant force. You're looking for redundant force. So how do you know how much it should deflect under this unknown force? You don't. You don't know. But what you can do is you assume that I have a unit force, a magnitude of 1 force there, pushing this point upward. And because it's a linear structures, so the actual deformations will be that unit force deflections times the magnitude of the force, By. By is an unknown. So you don't need to calculate By, but you calculate deflections under unit force. That you can calculate, right? So this is down, this is up, and one pushing down, one pushing up. So if they just equal to each other, then point B is undisturbed, unmoved. So the equations goes like that. Delta B plus By times FBB equal to 0. FBB is the flexibility coefficients that we introduced in the last chapter, the end of the last chapter. It's called flexibility coefficients. Loading at B, displacement at B. The loading is magnitude of 1, and displacement at B. So this is called flexibility coefficients. Okay, so the compatibility equations is the displacement due to the external force and the displacement due to the redundant force sum up should be equal to 0. Now be careful that the displacement that we talk about has a directional factors there. That means that positive is upward, negative is downward, right? So positive upward, so this is positive, negative downward, so this is negative, so that's why you can cancel them, right? Now, operations. In operation, how do you operate? Now, this is easy. You can do that. Can you calculate this delta B under this loading? This is determinate structure. Well, you have several ways you can do it. What? Can anybody tell me the ways to do it? Calculating displacements under loading? I should do a reverse checking. Huh? Who is here? What is your name? Huh? How about that? How many of you here? Not too many. Only 10. Oh, roughly only about 30 of you. Nice, good students. Huh? I should reward you, right? Huh? So let me do a reverse checking then. What is your name? The yellow shirt? Huh? Law, L-A-W. Oh, okay, got it. I record a positive sign there. Okay, I'll cancel it if you cannot answer my questions. All right. So, can you give me a method that you can use to calculate delta B under loading P? Just one. You don't need to give me too many. Oh, good. Virtual principle. You have positive. How about you? Next. Yeah, your name first. L-I-U. Oh, okay, got it. Okay. Another method. Yeah. Huh? Castigliano theories. Oh, good. Positive. Next. What's your name? Huh? L-M? L-A-M. They all start. You start with L. Then Chung Yun Wun. Then Chuck Wun, right? Oh, Julian. Oh, okay. Julian. Okay. Third method. Moment area. Good. Confirm. You. Conjugate beams. What's your name? Wang Chong Kai. Wang Chong Kai. Oh, okay. Confirm. Oh, it's too slow. I finished all. It's too slow. Yeah, 有咩办法呢? How do I reward you guys? Sign your name. How about that? Huh? Good. Anybody got a piece of paper? White paper? Good. Nah, it's not. Anybody got a blank paper? Oh, got it. Put down your name and your student ID. I will put the records there. Okay, where are we? Okay. So, here, this one, you can utilize all the methods that we introduced before, from direct integrations, moment area, conjugate beams, and more sophisticated energy principles, virtual principles, Castigliano theories. So at least you can use 5 of them. There are 5 methods that can help you to do calculations. All right? The last method is just lookup table. In a textbook, the first page, you flip open, there's a table for you to look up. So yes, you can look it up as well. Same thing here. If you apply a unit force, magnitude of 1 there, you can also calculate the displacement. Exactly the same methods, right? You can use direct integration, moment